Okay, see myself Ravi Kumarti. Today concept is Otto Cycle. I'm explaining obtain the expression for efficiency of Otto Cycle. See, before going to the expressions of Otto Cycle, you should know what is Otto Cycle and how it works. Okay, so Otto Cycle is mainly for SI engine. SI means spark ignition engine, or it is the petrol engine. Petrol engine. See, this Otto Cycle is working on working on constant volume working on constant volume, means both heat addition and heat rejection will take place at constant volume process. See, in the Otto Cycle we'll be having a 4 process. So there are 4 processes. The first one is adiabatic compression, process 1 to 2, adiabatic compression. Second process 2 to 3 is constant volume heat addition, Next process 3 to 4 adiabatic expansion, process 4 to 1 constant volume heat rejection. So these are the main important process is there in the Otto Cycle. So first one is adiabatic compression, second one constant volume heat addition, third one adiabatic expansion, fourth one is constant volume heat rejection. So now let us write the PV and TS diagram for Otto Cycle. Okay, so this is PV. Okay, then we'll take TS diagram. Okay, so here first process is adiabatic compression. So adiabatic compression is 1 to 2. So how to represent it? Adiabatic compression means here the volume is reducing in adiabatic compression. See, from 1 to 2. Okay, process 1 to 2. See, volume is reducing. Next is constant volume heat addition process. Constant volume means the volume remains constant, then the heat addition will take place at constant volume. So this is 2 to 3, means here it represent V2 is equal to V3. Okay, so next again 3 to 4 is adiabatic expansion. So adiabatic expansion is its volume is increasing and pressure is reducing. Okay, this is 3 to 4. Next 4 to 1 is constant volume heat rejection process. So here V4 is equal to V1. Then so this gap is VC, means it's a clearance volume. Okay, so here the first one is adiabatic compression. Here this heat addition will take place. I'll take it as a Q in. Okay, so and 3 to 4 is adiabatic expansion, and 4 to 1 is heat rejection. So Q out, I'll take Q out. So Q in and Q out. Okay, so heat added and heat rejected. Okay, so this is the PV diagram of Otto Cycle. So now how to write the TS diagram similar way. So TS diagram, adiabatic means it's also called as isentropic compression. So in this we'll take entropy is constant. Okay, the entropy is constant. So I'll take entropy S1 So this is 1 and 2. Here take S1 is equal to S2. Okay, so next one is constant volume heat addition process. Constant volume heat addition means the temperature is gradually increases. Because heat addition is taking place. So this is point 3. Next, adiabatic expansion. So here also entropy is constant because it's an isentropic. Okay, so entropy is constant. I'll take 0.4. So here S3 is equal to S4. Next is heat rejection. Heat rejection means is going out, so temperature is reducing. Okay, so here there is a work done takes place that you're going to call work done during the compression. So I'll take WC. And here there is a work done is taking place, that is work done due to expansion. Okay, and 2 to 3 is a constant volume heat addition, then heat addition will takes place, that is Qn. Next 4 to 1 is constant volume heat rejection. I'll take it in Q out. Okay, you can draw an extra line. You can take V is equal to constant. You can draw extra line. So this is V is equal to constant. So this is the PV diagram for and TS diagram for Otto cycle. So now we shall look into a expression how to draw. Process 1 to 2 is adiabatic compression. Process 2 to 3 is constant volume heat addition. Process 3 to 4 is adiabatic expansion. 4 to 1 is constant volume heat rejection. So this is the PV and TS diagram of Otto cycle. So let us see how to find out the expression for Otto cycle. So first process is adiabatic compression. So adiabatic compression, so 1 to 2. So during this process, the insulating cap is brought in contact with the cylinder head. The piston moves from top dead center to bottom dead center. See, the piston start moving from bottom dead center to top dead center. So compressing the volume from V1 to V2, so therefore the temperature rises, here from 1 to 2. So here the adiabatic means the Q is 0. Okay, Q is constant. So for here you'll get the process is TV power gamma minus 1 is equal to constant. So TV gamma minus 1 is equal to constant. The gamma is adiabatic index. Okay, so if you write for 1 to 2, you'll get T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. So here V1 by T1 by T2 is equal to V2 by V1 gamma minus 1. Okay, or you can rewrite this T2 by T1 is equal to V1 by V2 gamma minus 1. Okay, so this is process 1 to 2. So next is process 2 to 3 is constant volume heat addition process. So this is 2 to 3. Okay, here here the water heat is added at constant volume. So it is added at constant volume. So how to write the heat expression? That is, will take Q in. So Q in is it is added. So it is mCV delta T, means M mass, CV specific heat at constant volume, next temperature difference. So mCV dt. So temperature difference is how you going to take. So this is a 2 to 3 is a constant heat addition process, constant volume heat addition process. See here, temperature is gradually increasing. So temperature difference you can take from 3 to 2, T3 minus T2. So here we'll take T3 minus T2. This is process 2 to 3. Okay. So next process is adiabatic adiabatic expansion. So process 3 to 4, adiabatic expansion process 3 to 4. So here also if Q is 0 means it is a isentropic process. Q is equal to 0, then Q is 0, then it is also TV over gamma minus 1 is equal to constant. So it means that T3 V3 gamma minus 1 is equal to T4 V4 gamma minus 1. So you can rewrite this T3 by T4 is equal to V4 by V3 gamma minus 1. Okay. Next process is constant volume heat rejection, that is 4 to 1. So here similarly whatever we written in constant volume heat addition, so here also same thing. So here Q out which is equal to mCV. So here temperature difference you need to take means T1 T4 is there. So here temperature is gradually decreasing from 4 to 1. So you can take T4 minus T1, T4 minus T1. Okay. So these are the process. Process 1 to 2 is adiabatic compression. Next is 2 to 3 constant volume heat addition. Next is 3 to 4 adiabatic expansion. Next is 4 to 1 constant volume heat rejection process. So next, our main intention is to derive the expression for efficiency of Otto cycle. So what is the efficiency? Efficiency of Otto cycle. So efficiency is, what is the definition of efficiency? So definition of efficiency is work done by heat supply. Work done by heat supplied. Work done by heat supplied. So here you'll get heat supplied in constant volume heat addition, heat rejection in constant volume heat rejection, constant volume heat rejection. So work done means if you take a difference of Q in and Q out, you will get the work done in the Otto cycle. So therefore work done is equal to, you can rewrite Q in minus Q out. Q in means heat supplied, Q out means heat rejection, divided by Q in. Okay. So then you can rewrite the efficiency of Otto cycle 1 minus Q out divided by Q in. Okay. So which is also equal to 1 minus Q out means Q out, what heat rejection is mCV T4 minus T1. So mCV T4 minus T1, and Q in is, here we will get mCV T3 minus T2. mCV T3 minus T2. Okay. So therefore Otto cycle is, I'll cancel out m and CV, then I'll get 1 minus T4 minus T1 divided by T3 minus T2. Sorry, T4 minus T1 divided by T3 minus T2. See, you can alter again this Otto cycle equation, this 1 minus T4 minus T1 divided by T3 minus T2. See, you can take T1 out, that is T4 divided by T1 minus 1 into T1, then divided by T3. Here I can take T2 is out. Okay. So that is T3 by T2 minus 1 into T2. Okay. So we shall see the expression for T4 by T1 and as well as the T3 by T2. So we shall look into a first equation. So that is, first process 1 to 2 is adiabatic compression. So you can take an equation as, that is T2 by T1 is equal to V1 by V2 gamma minus 1. Okay. But from the diagram we can see that V2 is equal to V3, V4 is equal to V1. Okay, so from the diagram, from the figure, V1 is equal to V4, V2 equals V3. You can substitute there, therefore T2 by T1 is equal to V1 means V4, V2 means V3 gamma minus 1. But from process 3 to 4, because 3 to 4 is adiabatic expansion, so you will get the equation is T3 by T4 is equal to V4 by V3 gamma minus 1. Okay, T3 by T4 is equal to V4 by V3 gamma minus 1. So therefore T2 by T1 is equal to T3 by T4, which is equal to V4 by V3 gamma minus 1. Okay, so then you can alter this T2 by T3 is equal to T3, T2 by T3 is equal to T1 by T4. Okay, so I required here T4 by T1 and as well as a T3 by T2. I need to make it equal. So here you can rewrite this T3 by T2 is equal to T4 by T1. Okay, so here I can cancel this T4 by T1 and as well as the T3 by T2 because these two are equal. So therefore the equation may be reduced to 1 minus T1 by T2. Okay, so but from the process 1 to 2, T1 by T2 is equal to V2 by V1 gamma minus 1. T1 by T2 is equal to V2 by V1 gamma minus 1. So as we know the definitions of compression ratio, so that is RC, compression ratio, RC is beginning of the compression to the end of the compression. Volume at beginning of the compression and volume at end of the compression. So beginning of the compression is V1, end of the compression is V4. End of the compression is V2. Beginning of the compression is V1, end of the compression is V2. So therefore you can rewrite this, the above equation. The efficiency of the Otto cycle is equal to, so you will get T1 by T2 is V2 by V1 gamma minus 1. So here you will be having T1 by T2, so 1 minus V2 by V1 gamma minus 1, but our RC is V1 by V2. You can take it as a V1 by V2 gamma minus 1. So therefore you can rewrite 1 minus 1 by RC power gamma minus 1. This is the final expression of Otto cycle. So this is the efficiency of the Otto cycle. We shall see what is the expression required for mean effective pressure. So mean effective pressure of Otto cycle. Mean effective pressure, also called as MEP. Okay, so MEP definition is MEP is equal to PM is equal to work done per cycle divided by swept volume So therefore work done by cycle means Q in minus Q out. So this is the work done by the cycle. What is the swept volume? So means that distance traveled by the piston is called as swept volume. So from the diagram you can see that distance travel is 1 to 2, so you can take a V1 minus V2, so this is called as a swept volume. This is called as a swept volume, and this is a compression volume, and this is swept volume. Oh sorry, this is a clearance volume, I'm sorry, this is a clearance volume, and this is called as a swept volume. Okay, so swept volume. So this is the, here you can take a V1 minus V2. This is the MEP of Otto cycle. So if you write the total expression by deriving all these things, so you'll get the MEP of Otto cycle is, so this is the MEP of Otto cycle, and this is the efficiency of Otto cycle. So thank you. I'll do next problems on Otto cycle.